Sir, no.
It's a full screen.
Yes, yes,
Hmm?
yes, sir.
Okay. So, good evening, respected organizers, fellow scientists, and dear participants. It is a pleasure to be here in this winter school program to discuss a topic that is becoming central to the future of animal agriculture: climate smart livestock production for sustainable rural livelihoods. Today's lecture focuses on smart livestock production, a concept that integrates animal productivity, climate resilience, and environmental sustainability. Livestock is central to rural livelihoods, nutrition, and agricultural GDP. Yet, it is also highly vulnerable to climate stress and contributes to greenhouse gas emissions. So, the challenge before us is dual. We must increase production to feed a growing population while reducing environmental impact and making animals resilient to heat, diseases, and feed scarcity. This is not just a technical issue, it is a food security and sustainability issue. FAO defines climate smart agriculture based on three pillars: productivity, adaptation, and mitigation, while also supporting national food security in livestock systems. Productivity means higher milk, meat, and egg output. Adaptation means animals that tolerate thermal stress, disease challenge, and nutritional fluctuations. Mitigation refers to lowering methane and nitrous oxide emissions. Notice that these three pillars are interlinked. Improving feed efficiencies both increases productivity and reduces methane emission intensity. Livestock provides 17% of global calories and over one third of protein, making it nutritionally indispensable. But beyond nutrition, livestock shapes land use, biomass consumption, and nitrogen cycling. It also contributes about 40% of global agricultural GDP. This scale explains why livestock systems cannot be ignored in climate policy. They sit at the intersection of food, environment, and economy. Livestock consumes more than 35% of cereals and nearly 60% of global biomass harvest. It occupies 30% of the Earth's land surface and 70% of agricultural land and accounts for significant water use. These numbers show livestock's environmental footprint. Therefore, improving resource use efficiencies, more output per unit feed, land, and water is key to sustainability. From 1960 to 2025, per capita meat consumable tripled in developing countries, milk double, and eggs consumptions increased fivefold. This reflects increasing income, urbanization, and dietary transitions toward animal protein. Global population is projected to reach nearly 9.6 billion by 2050. Demand for beef, dairy, poultry, pork, and eggs is expected to rise drastically. This growth means we must intensify livestock systems, but intensification must be sustainable, otherwise, emissions and resource depletion will rise. Livestock contributes 20 to 18% of anthropogenic greenhouse gases, methane from human fermentation, nitrous oxide from manure, and carbon dioxide from feed production. Importantly, methane represents a loss of dietary energy. So, reducing methane is both an environmental and production efficiency strategy. Direct emissions come from enteric fermentation and manure. Indirect emissions arise from feed cultivation, fertilizer use, and land use changes. Feed production alone accounts for a large share, thus, feeding strategies are one of the fastest mitigation tools. Land use change contribute significantly, followed by animal production and feed production. Processing and transport are minimal. Therefore, livestock mitigation must focus at the farm and biological level rather than post-farming processes. Emissions intensity varies by uh, um, Species highest in beef, lower in pork and poultry, and lowest per kg of milk. Low yield dairy systems emit more greenhouse gases per unit milk than high yield systems. Hence, genetic improvement and feed efficiency reduces emissions intensity. This slide clearly demonstrates how productivity affects emission intensity. At very low milk yield levels, emission per kg of milk can be extremely high, sometimes 10 times higher than in high producing systems. This happens because maintenance energy emissions remains constant while output is low. So improving genetics, nutrition and health not only increase milk yield but also reduces emissions per unit of product. This is why efficiency is a mitigation strategy. This figure shows regional methane emission densities. Areas with large ruminant population and low feed efficiencies have higher emissions densities. This also indicates where mitigation efforts should be prioritized. Regions with high density and low productivity offer the greatest improvement potential. Atmospheric CO2 has increased by about 24% since 1860. Methane has doubled and global temperature are rising. These changes are not theoretical, they are already altering livestock production conditions worldwide. This slide gives real examples from India, drought and floods causing massive cattle losses. These events show climate change is not just future risk, it is already affecting animal survival and farmer livelihoods. Global warming is the cause, climate change is the effect. Okay. Global warming is the cause, climate change is the effect. Animal experiences these stress affecting health, reproduction, and nutrition, leading to poor performance and inferior product quality. Climate change thus directly reduces productivity. Direct impacts are physiological, heat stress, reduced intake. Indirect impacts include reduced soil fertility, poor feed crop yields, and disease spread. So, livestock is affected through both biological and environmental pathways. Feed intake declines once temperature exceeds comfort limits. At 35 degrees centigrade, intake can drop up to 35%. This is a protective survival response, but leads to productivity loss. Heat stress alters thyroid hormones, reduces metabolic rate, and increase cortisol and catecholamines. These hormonal shifts change energy metabolism and stress response. Uh, Under heat stress, animals enter a state of negative energy balance. Maintenance energy requirements increase by nearly 20 to 30% because animals must dissipate excess body heat through respiration and sweating. At the same time, nutrient absorption decreases and blood glucose levels falls. Increased circulating insulin under stress alters nutrient partitioning. Energy is diverted from production functions like milk synthesis toward maintenance and thermoregulation. This metabolic shift explains why milk yield and growth decline even when feed is available. Heat stress reduces saliva secretion. Saliva is a natural buffer. We all know that, which maintains rumen pH. Reduced buffering cause rumen acidosis, laminitis, and decline in milk fat. Fermentation shifts acetate production decreases while propionate proportion changes. This alters volatile fatty acid balance, reducing energy supply for milk fat synthesis. So heat stress affects not only quantity of milk but also its composition. Reproductive performance is highly sensitive to thermal stress. Hormonal imbalance reduces progesterone levels and affects ovarian follicle quality. Estrus expression becomes weak and short, making detection difficult. Early embryonic mortality increases due to high uterine temperature. In males, heat stress impairs spermatogenesis, reducing semen quality and libido. Thus, fertility decline under climate change is both female and male mediated. Heat stress suppresses human function, cortisol level increase, which downregulates immune cell activity. Cholesterol, immunoglobulin concentration falls, weakening passive immunity in newborns. High temperature also increase mycotoxin contamination in feed, further compromising immunity. As immunity declines, animals become more susceptible to infectious diseases. Milk production also decreases due to two major components. About 35% reduction comes from decreased feed intake and 65% from direct physiological stress. Milk product protein and solid non-fat SNF content decline. Economic losses are substantial, as shown by national level production loss estimates. Thus, thermal stress is a major threat to dairy profitability. India already faces severe fodder deficiencies, especially green fodder and concentrates. Climate change further reduces forage yield and quality by 10 to 20% in tropical regions. Reduced pasture productivity increases feed costs and decreases nutritional availability, compounding animal stress. Climate variability alters pasture composition and nutritional quality. High temperature reduces protein content and increase fiber, lowering digestibility, and as well the price of feed increases as supply declines. Thus, creates a feedback loop where poor nutrition versus heat stress effects. Physiological disturbances due to stress lead to cardiovascular strain, liver dysfunction, oxidative stress, and poor body condition, reduce nutrient absorption and metabolic imbalance, weaken animals, increasing disease risk and mortality. This is an institute that's a national initiative on climate resilient agriculture. Uh, is a is a national program in India focusing on climate resilience in agriculture. For livestock, NDRI works on production aspects and IVRI on disease aspects. These two are national institute which are to be deemed university, NDRI and IVRI. This initiative recognizes that adaptation must combine genetics, management, and disease control. The objective includes identifying heat tolerant indigenous breeds, studying genetic adaptation, discovering molecular markers for stress resistance, and developing disease forecasting models. The program also emphasizes technology dissemination and farmer awareness because adaptation is not only laboratory based but also field based. These are mitigation strategies which are grouped into management, nutrition, and technological approaches. These include grazing management, breeding, improved nutrition, agroforestry, manure management, and microbial intervention. Each strategy targets methane reduction, improved efficiency, or carbon sequestration. Coming to grazing management, reducing grazing pressure prevents land degradation and improve pasture carbon sequestration. Rotational grazing improves regrowth and reduce methane emissions per unit of live weight gain. Mobility of herds such as transhumans helps adapt to variable climates. Land tenure reforms may be required to maintain mobility pathways. Selecting more productive animals lowers methane intensity per unit product. Crossbreeding with locally adapted breeds maintain heat tolerance and disease resistance. There are so many crossbred which are used to be developed from early 90s, And so for the genetic improvement, it is a long term mitigation tool that permanently reduce emission intensity. Replacing natural pasture uh, with the improved digestible forage increases feed quality and animal productivity. Deep rooted grasses improve soil carbon storage and reduce enteric methane per unit of uh, per, uh, hmm, per unit of uh, output. Pasture intensification is both a mitigation and adaptation strategy. Increasing lipid content in diets suppresses methanogens and reduce methane production. Oils like sunflower, linseed, and coconut oil have shown significant methane reductions. However, inclusion level must be controlled to avoid negative effects on digestion. Uh, This is another one of the strategies, agroforestry, which integrate trees with livestock production. Trees provide shade, reducing heat stress and improving animal comfort and productivity. They also supply fodder and contribute to carbon sequestration by improving microclimate and soil quality. Agroforestry supports both adaptation as well as mitigation simultaneously. It reduces overgrazing pressure and enhances ecosystem stability. Manure management is a crucial because stored manure products produces methane. Covering manure storage systems and capturing biogas can significantly reduce emissions while producing renewable energy. Reducing storage time, lowering moisture, and manure acidification also decreases methane formation. Thus, waste can become a resource rather than a pollutant. Protozoa in the human host methanogens, reducing protozoal populations through defonation lowers methane production. However, complete removal may affect digestion, so balanced microbial management is necessary. This highlights the importance of human microbiome manipulation as a mitigation tool. Biotechnological approaches include vaccines targeting methanogens, genetic engineering, and microbial manipulation. Methane vaccines aim to stimulate antibodies that suppress methanogens. Although still under research, such technology represents future mitigation potential. However, human microbial diversity and ecological replacement pose challenges. Uh, okay. Okay. Compounds such as tannins, saponins, and essential oils can reduce methane production by altering human fermentation and reducing protozoal population. Condensed tannins can reduce methane without significantly affecting digestibility. These natural additives offer eco-friendly mitigation options. Now, coming to the conclusion, livestock contribute significantly to environmental problems, but also holds large potentials for solutions. Climate smart livestock production integrates productivity, adaptation, and mitigation strategies. By improving feed efficiencies, genetics management, and technological adaptation, we can secure both environmental sustainability and rural livelihoods. Addressing climate change in livestock system is urgent and essential. Thank you. Hello.
Sir. Thank you so much, sir.
Okay.
Anyone who want to ask any question? Anyone?
Hello.